Welcome to week 5 of this introductory course on synchrotrons and X-ray free electron lasers. Last week, we finished our discussion of the generation of synchrotron light and its properties. This radiation, as it emerges from the source, be that a bending magnet or an insertion device, is, to a greater or lesser extent, both divergent and polychromatic. This week, we discuss how we manipulate this radiation at beamlines, including the role of the so-called front end, mirrors and other focusing optics, monochromators, including the suppression of harmonics, and finally, different types of photon detectors. This first video is primarily concerned with the most important features of the front end, and then a discussion of mirrors and other focusing optics. So, let us begin with an overview of elements of a beamline. The generic setup is shown schematically here, and is just one possible configuration, but most beamlines follow this concept more or less in general terms. In the discussions this week, we divide up the beamline into the front end, the primary optics, including mirrors and monochromators, and finally, beamline instrumentation. In other words, those components most commonly, though not necessarily always, found in the experimental hutch, the furthest point downstream of the beamline. The purpose of the front end is to clean up the source radiation before it impinges on the primary optics and other components. Its primary functions include monitoring the position of the X-ray beam, normally at 2 or more positions, so that the position and angle can be triangulated and the stability monitored, also allowing feedback to improve this if necessary. In most cases, very high energy gamma radiation up to the energy of the electrons within the storage ring is produced as an inevitable consequence of the electrons occasionally colliding with residual gas molecules that remain even at pressures as low as 10 to the minus 10 millibars. This radiation, although only generating a total power measured in a few tens of milliwatts throughout the entire facility, is highly ionizing and must be blocked. Due to the very high energies, Bremsstrahlung is not deflected by, for example, the first reflecting mirror, but will simply pass straight through it. So the desired synchrotron radiation, with photon energies typically well over 3 orders of magnitude lower, is deflected by the mirror, so the Bremsstrahlung blocker can be placed behind this mirror. The Bremsstrahlung blocker needs to be made of a block of heavy metal, typically tungsten, with a thickness measured in several tens of centimeters. Only such a dense obstacle is sufficient to absorb Bremsstrahlung. The acceptance angle of the beamline is defined by a beam-defining aperture, discussed in a little more detail shortly. Radiation in an unwanted spectral regime or region can also be removed using filters. Finally, in many but not all instances, a window that is transparent to the X-rays of interest for the beamline is placed as one of the final components of the front end, in order to protect and isolate the storage ring in case the vacuum at the beamline suddenly fails, thereby preventing the entire ring from venting, which results in the entire facility being out of operation for days. Beam position monitors can come in various shapes, sizes and working principles. The simplest is simply a thin wire that can be traversed across the beam, which generates a photocurrent proportional to that beam intensity. This provides one coordinate of the beam position. The orthogonal coordinate can be obtained by placing a second wire monitor at 90 degrees to the first. Both X and Y coordinates can be simultaneously determined using 4 blades in a configuration as shown here. The beam halo is sufficiently intense to generate a photocurrent in the blades. By moving the four blades together left, right and up, down, the difference in the photocurrent between oppositely facing pairs can be equalized using comparator electronics and the beam position thereby determined. Lastly, a more modern approach is to use thin transparent windows, often diamond, coated with an array of ultra-thin metallic pads. This delivers not only directly the beam position, but also the profile of the beam. The acceptance angle of the source needs to be defined. This is obvious in the case of bending magnet sources, as they sweep angles far larger than typically desired for experiments, as we discussed last week. Even for undulators, however, the radiation does not immediately fall to zero outside the angles plus or minus 1 upon gamma, but instead contains a substantial amount of radiation, especially of soft X-rays. Remember, it's the soft X-rays that interact most strongly with matter, so often, at least in the case of hard X-ray beamlines, the aperture cuts this out. In order to cope with the high heat load associated with this, the aperture is normally conical, thereby spreading the absorbed energy over a larger area and is water-cooled. Nonetheless, the central part of the beam that passes through the aperture may still contain an unacceptably large fraction of unwanted X-rays, usually soft X-rays, that need to be removed. This can only be performed using a high-pass absorption filter. The specifications for this are very strict. It should efficiently absorb soft X-rays, typically up to approximately 5 kilo-electron volts, and will thus heat up substantially, meaning the filter must have a high melting temperature and remain mechanically robust. This heat also needs to be efficiently dissipated, requiring good thermal conductivity. Essentially, there is only one material that fits all of these requirements: diamond, which, incidentally, is the best-known heat conductor, even surpassing the conductivity of copper or silver. Thin, artificially grown diamond windows are commercially available and can be brazed onto a water-cooled vacuum flange, as shown here. Obviously, this high-pass filter is not used for beamlines operating the tender or soft X-ray regime. We now turn our attention to the primary optics and other focusing elements. For the remainder of this video, we will discuss X-ray mirrors and X-ray focusing elements. The topic of monochromators will be dealt with separately in the next video. The primary optics typically include one or more mirrors, which may or may not also focus, plus a dispersive instrument, the monochromator, used to select a certain, normally narrow, range of wavelengths. In the second week of this course, we establish that at sufficiently shallow incident angles, X-rays can be made to reflect off a flat surface via total external reflection. The upper limit to the incident angle, you will remember, is given by the critical angle alpha c, which is equal to the square root of 2 delta, where delta is the refractive index decrement. Delta is itself directly proportional to the electron density ρ of the reflecting material and to the square of the X-ray wavelength, and thus inversely proportional to the square of the wave vector or photon energy. So alpha c decreases as 1 upon the photon energy and increases with the square root of the electron density. Now, even the most collimated synchrotron beam has a finite cross-section with a height typically of the order of 1 millimeter at the primary optics, which may be 20 meters or further downstream of the source. This means as the photon energy increases, the critical angle gets smaller and the footprint of the beam becomes longer and longer as one is forced to reduce the incident angle. Below an angle, given in radians, equal to the beam height divided by the length of the mirror, normally measured in a few tens of centimeters, in other words, a few milliradians, or between 0.1 and 0.2 degrees, a substantial fraction of the beam will spill over the ends of the mirror. Normally, fabrication of the X-ray mirror is limited to approximately a meter or less. This overspill problem is resolved not by making longer and longer mirrors, but instead by coating the mirror. The mirror is almost always made either from silicon or fused silica glass, and the coatings are some high-density material, most commonly rhodium and/or platinum. And this bumps up the critical angle, which, we've just reiterated, is proportional to the square root of the electron density. Mirrors thus commonly have stripes of coatings of different densities, so by a simple lateral movement of them, one can switch from one material to another on the same mirror surface. So, for example, the uncoated part of a silicon mirror has a critical angle approximately 3 times smaller than that part coated with a platinum layer. This aspect of the energy dependence of the critical angle can be used to advantage. When one selects a certain photon energy, hν, using a monochromator at a beamline, harmonics of this radiation, that is at 2hν, 3hν, etc., etc., will also be selected. Radiation from synchrotrons is polychromatic. In the case of bending magnets and wigglers, it is broadband, but even for undulators, the maxima are integer multiples, m, of the fundamental energy. Therefore, harmonic signal will also pass through to the beamline unless measures are taken to circumvent this. Some other strategies are detailed in the second video of this week, but one of the most effective ways to achieve harmonic suppression is explained here in the context of mirror reflectivity. Let's consider a particular photon energy, highlighted here with the red arrow. If we set the incident angle to be only marginally below the critical angle for the mirror at this photon energy, then the double of this energy, i.e. the second harmonic, shown here in green, will have its critical angle below the incident angle and will only be inefficiently reflected. The third harmonic, here shown in blue, will be still less reflected. As an example, a silicon mirror tilted at an angle of 0.2 degrees will efficiently reflect 8 kiloelectron volts radiation, for which the critical angle is 0.23 degrees. However, the critical angles for the second harmonic at 16 kiloelectron volts and the third harmonic at 24 kiloelectron volts are 0.114 and 0.076 degrees respectively. Both of these are now above the incident angle. As a result, their reflectivities are approximately 8 times 10 to the minus 3 and 1.4 times 10 to the minus 3 respectively. Now, in many instances, such as in most diffraction experiments, a still higher degree of harmonic rejection is required. One commonly used approach is to allow the radiation to bounce off not just one, but a second mirror at the same angle, thus squaring the degree of reflectivity, which in this instance would be 6.4 times 10 to the minus 5 and 2 times 10 to the minus 6 respectively for the second and third harmonics. Before we move on to discuss aspects of focusing, it's briefly mentioned here that the reason that mirrors are not fabricated with lengths much more than a meter is because their quality deteriorates. The two main properties defining mirror quality are the so-called slope error, that is, the amount of wobbliness of the surface over macroscopic distances, and this is typically measured in microradians. The second property is the atomic roughness, measured in a few angstroms. Now, this doesn't mean necessarily that the surface needs to be atomically flat without any imperfections along the entire length of the mirror on an atomic level, but it should maintain, on average, the desired specifications within at least 1 or 2 multiples of the coherence lengths of the radiation being reflected, which thus can be of the order of several hundred microns in the case of transverse coherence. We now turn to aspects of X-ray focusing. Before we discuss specific examples, some fundamental features need to be clarified. The two shapes of primary concern for us will be the ellipse and the parabola, and in a moment, their spherical or cylindrical approximations. Ellipses and parabolas are conic sections. An ellipse is a section for which the sectional plane subtends an angle greater than phi with the cone axis, where phi is the opening half angle of that cone. A parabola is described by the intersection between a cone and a plane for which the cone axis plane angle is exactly equal to phi. Their mathematical equations are shown here. Ellipses and parabolas are interesting because, when using ray optics, they can focus to an exact point. Note that ray optics actually don't really represent reality, as diffraction effects, in other words, aspects of wave optics, means that no focal spot can be of 0 size. Nonetheless, diffraction effects excluded, these shapes are in principle aberration-free. An ellipse will focus a point source to a point focus if the source lies on one of the foci of the ellipse, plus or minus f prime. Here, the prime is used as this is not the same as the focal length, denoted by simply f. The distance defined by the reflected rays between the source and the image are all equal in length. Indeed, you may remember that one can draw an ellipse by pinning down a piece of string at 2 points, which then define the foci, and then putting the string under tension with a pencil and moving this from one end to the other. Now, consider the symmetrical path between the foci, highlighted here in red. This path subtends the shallowest angle with the ellipse where it is reflected. This angle is equal to the arctangent of b divided by f prime, and needs to be shallower than the critical angle for total external reflection. It is therefore clear that b must be much smaller than f prime by about 3 orders of magnitude. In this case, f prime is approximately equal to a, the semi-major axis. In other words, the foci are exceedingly close to the left and right-hand apexes of the ellipse, and the ellipse is much, much wider than it is high. Ellipses are therefore excellent shapes for refocusing a small source via reflection. Parabolas, on the other hand, focus parallel light to a point, as shown here on the right-hand side. Although some optics are indeed manufactured to have either an elliptical or parabolic profile, especially secondary optical elements, it's technologically very demanding to fabricate mirrors and larger focusing elements with exactly these shapes. Instead, one often approximates the surface of ellipses and parabolas with that of a circle or sphere for two-dimensionally focusing elements. It can be shown, for example, that a cylindrical surface with a radius rm equal to a squared upon b has only a very marginal deviation from the elliptical surface at the symmetrical reflection point, which was shown in red in the last slide. Similarly, a circle with radius 2f closely approximates the profile of a parabola of the form x squared upon a at its apex. The geometric ray optics described until now, in which a point source can be perfectly focused to another point, are, unsurprisingly, unachievable. Due to diffraction, no beam with a Gaussian profile can be focused to a perfect point with no physical extent, but instead will have a minimum beam waist diameter 2W0 shown here. The Rayleigh length ZR is the distance along the propagation direction z between this waist and where the beam's linear extent is larger by a factor of the square root of 2. In other words, where the beam cross-section increases by a factor of 2. And is given by ZR is equal to pi W0 squared divided by lambda, where lambda is the beam's wavelength. The validity of this equation assumes that W0 remains significantly larger than lambda, which certainly holds true for hard X radiation of wavelengths of the order of an angstrom. The depth of field is twice ZR. The beam radius WZ at a distance z from the beam waist is given by WZ is equal to W0 multiplied by the square root of 1 plus z upon ZR squared. From this, it can be demonstrated that the full width half maximum divergence, big theta, is related to W0 and ZR by theta equals 2W0 divided by ZR. Using this relationship and substituting for either ZR or W0, their relationship to the beam divergence can be derived, as shown here. The more focused the beam, i.e. large theta, the smaller the focal spot and the shorter the depth of field. As an example, a Gaussian beam of 1 angstrom radiation focused using parabolic optics with big theta equals 10 milliradians or 0.57 degrees will produce a spot size of 6.4 nanometers with a depth of field of 2.55 microns. A 10 times more gentle focus of theta equals 1 milliradian can only be focused to 64 nanometers minimum size, although the depth of field will increase 100-fold to 255 microns. Hence, the cost of strong demagnification is thus an accompanying rapid inverse square reduction in the depth of field. The lensmaker equation states that the reciprocal of the focus of a lens, 1 upon f, equals the sum of the reciprocals of the source to lens distance, p, and the lens to image distance, q. The degree of magnification is q divided by p. Hence, values greater than unity will blow up the image size compared to the source, while demagnification with q upon p less than unity will focus down the image to sizes smaller than the source. Note also that an m-fold demagnification, q upon p is equal to 1 upon m, will be accompanied by an m-fold increase in beam divergence, and vice versa. This is merely a restatement of the fact that the beam emittance will remain constant. The Coddington equations relate P, Q, and F with the bending radii Rm and Rs. Rm is the meridional bending radius in the plane perpendicular to the mirror or reflecting element, including, for example, a diffracting crystal, which also includes the beam axis. Rm thus focuses in the transverse plane perpendicular to the bending plane, which in the case shown here is the vertical direction. RS is the sagittal bending radius required to focus in the direction perpendicular to the meridional focusing, in this case horizontally. As we should now know, theta is in general small for mirrors, as will therefore be sine theta. Hence Rm for mirrors are typically measured in kilometers, while Rs, which is directly proportional to sine theta, may only be a few centimeters. Now, focusing can also be achieved by bending gratings or crystals in monochromators, as we will see in the next video. In general, the incident angles on dispersive monochromator elements is larger, and the meridional and sagittal radius less radically different from each other when using these elements. A convenient shape for achieving sagittal and meridional focusing in just one element is the toroidal mirror. This is a cap section of a ring torus with ring radius Rs and torus outer radius Rm, as shown here. As Rm is in general significantly larger than Rs, particularly for mirrors, the ring torus is very thin, much like a bicycle in a tube. In general, toroidal mirrors have fixed surfaces machined out of a solid block of material. That is, neither Rm or Rs can be varied. Kirkpatrick bias or KB mirrors provide independent orthogonal focusing using two cylindrically bent surfaces. This has the advantage that vertical and horizontal focusing are decoupled. Indeed, it is possible to dynamically bend the mirrors using a flexor system, thus allowing adjustment of the position of the focal spot. The separation of focusing into two stages does, however, make KB mirrors more bulky. We finish this video with a discussion of refractive and diffractive focusing elements. Compound refractive lenses, or CRLs, in their simplest form consist of holes drilled out of transparent materials such as beryllium, transparent for X-rays that is. The focal length is given by the hole radius r divided by 2 times the number of holes nh and the refractive index decrement delta. This last parameter is equal to about 2 times 10 to the minus 6 for beryllium at 12 kiloelectron volts. Hence, a CRL consisting of an array of 30 200 micron diameter holes has a focal length of approximately 70 centimeters. CRLs have the advantage that they are easy to align in the X-ray beam, they don't divert the beam axis, and elements can be stacked after one another to change the focal length. Their main disadvantages are A, that the focal length is proportional to the square of the X-ray photon energy, which means that they must be repositioned, restacked, or replaced if the photon energy has changed, and B, that the transmission is in general fairly poor. A 100-hole CRL made of beryllium with walls of 100 micron thickness separating adjacent holes has a transmission of only 0.5 at 12 kiloelectron volts. In addition, because refraction of X-rays is so weak, the hole diameter, big R, needs to be quite small in order to achieve a reasonably short focal length. But this can often mean that the beam propagates through the sides of the holes, where the deviations from a parabola are large, resulting in significant optical aberrations. Much effort has been made in recent years to fabricate CRLs with parabolic surfaces, using sophisticated mechanical milling or even focused ion beam milling. Lastly, the choice of materials depends on the photon energy range for which the CRL is being manufactured, the required focal length, and the acceptable loss in flux due to absorption through the lenses themselves. So, for example, although the attenuation length of diamond at, let's say, 15 kiloelectron volts is 5 times smaller than for beryllium, its refractive index decrement is more than double than that of beryllium. Fresnel zone plates, or FZPs, are diffractive focusing lenses consisting of a set of concentric rings. These rings can either be opaque, in which case light passes through the gaps in between them, or in the case of so-called phase FZPs, they have a specific height for the thicker rings in order to enhance diffractive effects by adjustment of the optical path length. The general approach of FZPs is to design them so that light being scattered as it passes through different parts of the FZP will always have an integer number of wavelengths path difference at the focal spot. So, in the figure shown here, light passing along path Pn+2 will be longer than that passing through Pn by an integer number of wavelengths. The conditions for constructive interference, and thus the radii of the rings in an FZP, are given here. See also the website given at the bottom for a more detailed description. The width of the outermost ring, delta R big N, is equal to the square root of the wavelength times the focal length divided by large N, the total number of rings. An FZP of diameter R big N is equal to 100 microns, consisting of 4,000 rings, will have an outer ring thickness of 50 nanometers. Such a delicate structure is synthesized by electron beam lithography. Note also that the ultimate resolution of an FZP is determined by delta R big N, the outer ring thickness, and is equal to a value a little more than this by a factor of 1.22. FZPs are used when requiring the tightest focus, and values in the range of a few tens of nanometers for hard X-rays have been achieved recently. Lastly, it should be noted that the inverse dependence of the focal length on lambda implies a linear dependence with photon energy. This is less severe than the square dependence of CRLs on energy, which can thus make FZPs more attractive for use with unmonochromatized X-FEL radiation, which can have a substantial bandwidth. The efficiency of FZPs is in general only moderate. The theoretical equations for this is given here for phase FZPs, where nu is the ratio between the absorption index beta and the refractive index decrement delta, and phi equals 2 pi delta t divided by lambda is the phase shift induced by the X-rays passing through a ring of thickness t. The actually achieved efficiency is in general lower than this, as this equation has assumed that the thin rings of the FZP actually have zero thickness. Summarizing this first video of week 5, we have covered the function of the front end, features of both reflecting and focusing mirrors, plus a description of compound refractive lenses and Fresnel zone plates. In the next video, we cover monochromatization of synchrotron radiation using gratings, crystals, or multilayers.